In chapter 6, we're going to start talking about inferences that we can make for data. And we're going to start with categorical data, which is proportions. And in the first section, we're going to talk about confidence intervals. So let's talk about what a confidence interval is. So if we want to estimate the value of some parameter from a population, we can take a sample and calculate a statistic from that sample. And we know that the sample statistic is an estimate of the population parameter. And we know from previous chapters that selecting different samples will yield different statistics and therefore different estimates for the population parameter. Therefore, it would make more sense to, instead of just giving one estimate of the population parameter, to give an interval of plausible values. Based on the sample data. And that's what a confidence interval is. It's that interval of plausible values. So for example, something you might want to make an interval for is pulling cards out of deck of 100, the proportion that are the same color, where each person pulls out 10 cards, you record the proportion of pink. So you don't know what the population proportion of pink cards is, much like real life. So we want to know, is our distribution exactly equal to our population parameter? We assume it's going to be around p hat, but how close to p is it likely to be? So a couple of things we just want to review back from when we were talking about the normal distribution in chapter 1 is the 68, 95, 99.7 rule. So if you remember, 68% of our data is within 1 standard deviation of the mean, 95% is 2, and 99.7% is 3. And from chapter 5, we know the center of our distribution is equal to the population parameter. We know the shape is going to be normal, and we know the standard deviation formula is the square root of p times 1 minus p all over n. Now, obviously, we only know these things based on our conditions. So just to rewrite, 68% of our data is within 1 standard deviation of the mean. 95% is within 2 standard deviations of the mean, and 99.7% of the data is within 3 standard deviations of the mean. We also know that not all data is going to be between 1, 2, and 3 standard deviations of the mean. So a confidence interval, its definition is that a confidence interval for a population parameter is an interval of plausible values for that unknown parameter. And we construct it in such a way that with a chosen degree of confidence, the value of the parameter will be captured inside the interval. And that chosen degree of confidence is called the confidence level. And the confidence level gives us information about how much confidence we have in the method used to construct the interval. So another way to think about it is that a confidence level gives the long-term capture rate used to construct the interval. So if you're looking at some arbitrary percent confidence, so C percent confidence, and you're looking at an interval, it gives an interval of plausible values. For a parameter. And the way we construct that interval is from the data, and it's the form point estimate plus or minus your margin of error. And point estimate is just another way to say mean. So whether or not you're looking at a mean with proportions or a mean with means, whether it's a mean or a proportion, it's always whatever your sample statistic is plus or minus your margin of error. And we'll talk about here in a little bit what the formula for margin of error is. And then the difference between your point estimate and your true parameter value will be less than the margin of error in whatever percent, your C% of all samples. So as we said, confidence level C gives your long-term capture rate for calculating the confidence interval. So that tells you is in C% of all possible samples, the method would yield an interval that captures the true parameter value. In other words, if you repeat this process many times and calculate a confidence interval each time, C% of them will capture the true parameter. So when it comes to interpreting confidence levels and confidence intervals, we will write a sentence for every confidence interval we perform or calculate, and they're going to be very, very similar in the script. We'll say we are C% confidence that the interval from whatever your true value is captures the, and then whatever your parameter is in context. And then just kind of an example of what a confidence level means is if we take many samples of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. So that's kind of an example with a known confidence level instead of just saying C. So C, your confidence level, is not how likely it is that your interval contains it, but the percent of intervals constructed that are going to contain your parameter value. So on any given problem, you will definitely have to interpret the confidence interval. You may have to interpret the confidence level or even both. So make sure you understand the difference between a confidence interval and the confidence level. So now let's go ahead and talk about how we get to our margin of error. So we use something called a critical value. And the critical value is a multiplier that makes the interval wide enough to have whatever your stated capture rate is. So in other words, it's the number of standard deviations to have C% of the area in between. So that tells us to calculate our margin of error, you take your statistic and you add and subtract that critical value times your standard deviation. And the critical value times the standard deviation is the margin of error. So when we say margin of error, we mean critical value times your standard deviation. So a couple of things here. If you increase your confidence level, which increases your critical value, we want to talk about what happens to your margin of error. So if you want to be more confident, your margin of error, which I'm going to abbreviate ME, increases as confidence increases. Because you want to be more sure that your interval contains it, you're going to have a larger margin of error. So what that means is the interval gets wider. Okay. What happens if you decrease your confidence level? So you want to be less confident. That has the opposite effect. Your margin of error would decrease, which means the interval gets narrower. Let's talk about what happens when you look at standard deviation. So remember, the standard deviation for a proportion equals the square root of p times 1 minus p all over n. So we've talked about what happens with our margin of error, how that increases or decreases affected it. Now let's talk about our standard deviation. So what happens to margin of error as you increase sample size? Because sample size is going to be the one thing that is going to control your standard deviation, because your proportion is going to be set. So that's not really going to have an effect. So we've talked about this before. As you increase your sample size n, it decreases the standard deviation of your p hat, which means it also decreases your margin of error, because if the standard deviation gets smaller, then the margin of error would get smaller. On the reverse side of things, if we decrease sample size, then we increase our standard deviation, which means we increase our margin of error. So then our interval would get wider. So opposite effect as our critical value. So our critical value increases margin of error as it increases, but with standard deviation, as you increase n, it actually decreases margin of error. So no matter what we're doing, our goal is to have a small margin of error. We don't want there to be a very large margin of error in general. So there's two ways to do that. You can either decrease your confidence level, or you can increase your sample size. Now, we don't really want to decrease our confidence, because if we decrease our confidence, then our intervals are less likely to contain our true population parameter. So increasing our sample size is how we kind of offset that, making sure we have a large enough sample size so that no matter what level of confidence we're looking at, we don't get an overly large margin of error. So remember, when we are performing an inference, we're going to assume that our data is going to come from an SRS of your size n from your population of interest. And our margin of error in a confidence covers only chance variation due to that random sampling. So let's go ahead and take a look at an example that's kind of already created for us. So we have a New York Times / CBS News poll that asked a random sample of U.S. adults, do you favor an amendment to the Constitution that would permit organized prayer in public schools? And based on this poll, the 95% confidence interval for the population proportion who favors such an amendment is between 0.63 and 0.69. So the first thing we want to do is interpret the confidence interval. So what does it mean to have a confidence interval of 0.63 to 0.69? So the way that works is we start with we are, and then whatever percent confident, so 95% confident, that the interval 0.63 to 0.69 captures the true proportion of U.S. adults who favor the amendment. So it's the same sentence no matter what kind of confidence interval you're looking at. We are whatever percent confidence that the interval, whatever your interval is, captures the true proportion of whatever your scenario is. So it's the same setup for every confidence interval. You just plug in new information. So for B, if we're given our confidence interval, we want to know our point estimate or our mean, and then our margin of error. So in a confidence interval, the mean is in the middle. So I do 0.63 plus 0.69, and I divide by 2, and that will give me my p hat, which in this case is 0.66. And then my margin of error is then the distance from that mean to either side of the values of my confidence interval. So 0.66 to 0.69 is the distance of 0.03. Same thing of 0.63 to 0.66. So my margin of error is 0.03. Another way you can find the margin of error, subtract your interval, so 0.69 minus 0.63, then divide by 2. The last part asks us, based on this poll, a reporter claims that more than 2/3 of U.S. adults favor such an amendment. Use the confidence interval to evaluate this claim. So when you're doing something like that, you're looking at, does my confidence interval contain 2/3 or higher in its entirety? So 2/3 is 0.67. But my confidence interval goes from 0.63 to 0.69. So I can't explicitly say that more than 2/3, because there is a probability based on my interval that it is less than that. So it is incorrect because our confidence interval might be more than 2/3, but it could also be less than 2/3. If my confidence interval had been 0.67 to 0.75, sure, more than 2/3. Every value in that confidence interval is 2/3 or higher. But considering in our interval we go as low as 0.63, we're saying it could potentially be less than 2/3. Okay. Another example, kind of like a multiple choice type example. We have that a researcher plans to use a random sample of families to estimate the mean monthly family income for a large population. They are deciding between a 95% confidence level and a 99% confidence level. Compared to a 95% confidence interval, a 99% confidence interval will be narrower and involve a larger risk of being incorrect, wider and a smaller risk, narrower and a smaller risk, wider and a larger risk, or wider and would have the same risk. So let's first talk about narrower versus wider. So we know as you increase your confidence, you increase the width. All right? The more confident you are, the larger the width. So I know that it's not going to be narrower. So that narrows it down to B, D, and E. The other thing is, if I increase my confidence, it's going to have a different risk of being incorrect. It's not going to stay the same if I increase. So whenever we increase our confidence, we are saying our interval is more likely to contain our population, which means there is less of a chance of it being incorrect. So it's a wider interval, but it's a smaller risk of it being incorrect. So let's talk about our conditions. So just like when we were doing a sampling distribution for a proportion, we also have conditions for creating a confidence interval for a proportion. And the nice thing is they are the exact same conditions. So the first condition is random. So you either have to come from an SRS if sampling or random assignment if you're conducting an experiment. The second one is independent. in which case you have to check your 10% condition, which is that n is less than or equal to 0.10 of your population size. And then lastly, it has to be normal. So that was NP greater than or equal to 10 and n times 1 minus p greater than or equal to 10. So exact same conditions as we were looking at a sampling distribution. So now let's talk about how our formula changed. So when we were looking at a sampling distribution, we typically knew our population proportion. But in this case, we're not going to know p. We're only going to have p hat. So that changes my normal. So instead of doing n times p, we're going to have n times p hat and n times 1 minus p hat. We're only going to know our sample proportion p hat. We're not going to know a population. So this also affects our standard deviation. So it's no longer going to be known as standard deviation. It's going to be known as standard error because it's being based off your sample proportion p hat instead of a population proportion. So the only difference is that the standard deviation of p hat is now equal to the square root of p hat times 1 minus p hat all over n. Same formula, it's just instead of p, we have p hat. So we call it standard error when the standard deviation is estimated from sample data. And then remember, we also have our critical value, which is going to be our z-score that sets the boundary for our confidence interval. So how many standard deviations you want to go on either side. And we indicate that with a z and a little asterisk and an exponent. So let's talk about how we calculate that critical value. And I'm going to draw some pictures to kind of indicate how this works. So if I'm looking at something where I want to be 80% confident, so we go back to our normal distribution. We have two z-scores, a negative z-score and a positive z-score. And in the middle of those two z-scores contains our percentage, which in this case would be 80%. And if I want to find those z-scores, I use INV norm. And I look at the area below. So if we remember, the remaining area, 20%, is split up half above and below. So that means I have 10% above and 10% below. So we go to INV norm. Our area is 0.10. Our mean would be 0. Our standard deviation would be 1. And that's going to give us our negative z-score, which would be negative 1.28. And then when I do it for the upper, so my area being 0.90 with the mean and standard deviation, that's how I get my positive. We are going to always use the positive critical value and when we're identifying it. And I'll talk about more why we always use the positive one here in a second when we actually talk about what the formula is. But we'll always just use the positive critical value. So if I want to go with 90% confidence, so very, very similar, you have your negative z and your positive z, your area in between, which is 90%. Now this time, the remaining area, 10%, gets split up. So you have 5% above and below. So we go to INV norm. Our area is 0.05. Mean is 0. Standard deviation is 1. And we're going to get that our critical value is 1.645. Again, it would come out negative, but we're going to ignore the negative. For 95%, have our area in between, which is where we get 95%. And 5% is the remaining area. It gets split in half, and we get 2.5%, which is going to be 0.025. Which is going to give us a critical value of 1.96 when we use INV norm. And the last one is 99%. And so we have our negative critical value and our positive critical value. Our area in between, so 99%. And I'm left with 1% that gets split in half, which is 0.5%, which is 0.005. And when we use INV norm, we get a Z critical value of 2.58. These are the 4 most common confidence intervals we're going to calculate. They are by no means all-encompassing. Sometimes we might do 98%. Or something else, but use the same method every time to calculate your critical value. Use INV norm, you figure out the remaining area, split in half, and use INV norm. So let's talk about the formula. So as long as the conditions are met for your confidence interval, then we calculate it by doing p hat plus or minus your critical value, which we've now known is represents with the Z with the asterisk, times your standard deviation, which is the square root of p hat times 1 minus p hat all over n. So it just takes that basic formula we talked about at the beginning, point estimate plus or minus critical value times standard deviation, and now we're replacing it with what that information is. Our point estimate is p hat, our critical value is our Z score, and our standard deviation is our standard error. And this is called a one sample Z interval for proportions. So when it comes to doing a problem, just like we have the 4-step process for a sampling distribution, we have a 4-step process for a proportion. You're going to want to figure out what your P is and what your confidence level is and its critical value. You want to check your conditions. Once the conditions are met, you write down your formula and you substitute the values in. Now the actual calculating, you have 2 choices. You can do the rest of the math either by hand or in the calculator. So you go to calc and then you go over to tests and then you want the letter A, 1 prop Z int. It stands for one sample proportion Z interval. And then once you find your confidence interval, you'll then write your sentence with your conclusion. So let's go ahead and do a couple examples. So a Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. Construct and interpret a 95% confidence interval for the proportion of all teens who would say yes if asked this question. So first I want to find my Z critical value and my P hat, and I want to identify N. So because I am 95% confident, we know from the previous page that my Z critical value is going to be 1.96. They don't give me an explicit P hat, but they tell me how many out of the sample said yes. 246 out of 439. Now, this is not going to be a nice decimal, but we're going to round 2 decimal places, so 0.56. And then obviously N is 439. Okay. Now we're going to check our conditions. So the first condition we're going to check is random. And it does say that there was a random sample. So we're good there. Next we check independent. So 439 has to be less than or equal to 10% of all U.S. teens aged 13 to 17, which there's at least 4,000 of those, so we're good there. And then for normal, 439 times 0.56 has to be greater than or equal to 10, and 439 times 0.44 has to be greater than or equal to 10, which we're good, because half of 439 is over 200, so we're good there. Now comes the actual confidence interval part. So we use our formula. It says p hat, which is 0.56, plus or minus your critical value, 1.96, times the standard deviation, 0.56, times 0.44, all over 439. So here's where you have your choices. You can now do the math to calculate your confidence interval, or you can use the calculator. So I'm going to do the math first, and then I'll show you how to do the calculator. So I'm going to leave it as 0.56 plus or minus. That plus or minus indicates that we can have a positive or a negative z critical value. So that's why we use the positive z critical value when we do INV norm, is because I will take into account that it could be negative when I actually plug it into my confidence interval. So now I want to actually figure out what 1.96 times the square root of 0.56 times 0.44 over 439 is. In this decimal, I always went around 4 decimal places. So I get 0.0464, and now I'm going to add and subtract that from 0.56. So I do 0.56 minus 0.0464 first, because the left side of your confidence interval has to be the smaller number, so 0.5136. Then we do 0.56 plus 0.0464, and we get 0.6064. So that's option 1, where you do the math. Your second option is to use the calculator. And the way we get to that is we hit stat, and we go over to tests. So stat, tests, and then we want number 5, which is letter A, which is 1 prop z int. Okay. So it asks for 3 things: X, N, and your C level. X is the number of yeses in this case, so X is 246. N is your sample size, 439. And then the C level, it wants it as a decimal, which in this case is 0.95. So you plug in those 3 things. Then you hit calculate. And you only have to calculate once. And it's going to give us 0.5139, comma 0.6068. So it's fairly close to what we did when we did it by hand. It's a little bit more accurate because, one, I had to round my p hat when I calculated it, because 246 over 439 is not exactly 0.56. And secondly, my critical value isn't exactly 1.96. It's also rounded. So the calculator is actually more accurate because it doesn't do any rounding, but I would accept either one. And then our last step is to go ahead and write our sentence. So our sentence is, we are 95% confident that the interval 0.5136 to 0.6064 captures the true proportion of teens who would wait until marriage to have sex. Do one more example. In a random sample of 250 high school students, it was found that 85% of them later graduated. Find the 98% confidence interval for the true proportion of all high school students who graduate. So our confidence level is 98. So that is one critical value we didn't calculate before. So I'm going to go to second bars and I'm going to go to INV norm. So the remaining percent is 2. Half of 2 is 1. So my area is going to be 0.01. And I'm going to get 2.33. My p hat this time is given to me explicitly as 0.85. And n is 250. Now we're going to check our conditions. So for random, it does say there was a random sample. For independent, 250 has to be less than or equal to 10% of all high school students, which there's definitely at least 2,500 of those. There are some high schools that have just 2,500 students. And lastly, for normal, 250 times 0.85 has to be greater than or equal to 10, and 250 times 0.15 has to be greater than or equal to 10, which we're good there. Now we're going to do our formula. So p hat 0.85 plus or minus our critical value 2.33 times the square root of 0.85 times 0.15 all over 250. Now in this case, it actually isn't going to make much sense for me to use my calculator. Because I'm not explicitly given x, I would need to find out what 85% of 250 is. And if I do 250 times 0.85, I get 212.5. And the calculator will not accept a decimal for x. It will only accept whole numbers. So it is better for us in this case to use the formula than it is to use the calculator. And it works here because p hat is exactly 0.85, so the only time I'm really rounding is for my critical value. So I'm not really rounding multiple times like in the previous example. So we'll do 0.85 plus or minus, and then 2.33 times the square root of 0.85 times 0.15 over 250. And we're going to get 0.0526, which becomes 0.7974 when you subtract it, and 0.9026 when you add. So for our sentence, we are 98% confident that the interval 0.7974 to 0.9026 captures the true proportion of high school students who graduate. So the last thing we're going to talk about is necessary sample sizes for a specific margin of error. So it is very, very common that researchers limit the margin of error to a fixed amount to maintain a certain confidence level. So the only thing that can vary in those cases is the sample size, since the value for p hat is something that is out of our control. So in order to do that, we look at the components for margin of error. So we know margin of error is our critical value times our standard deviation, p hat times 1 minus p hat all over n. And if I want to get if I have a specific margin of error and a specific critical value, the only thing that I'm going to be able to control is n. So if I were to solve that formula for n, which I'm not going to show the algebra for it, but there is algebra. You divide by z critical value, you square it, you cross multiply. It's a lot of steps. But when I do that, I get that n equals your z critical value over the margin of error squared times p hat times 1 minus p hat. So from this, we would obviously be given our set margin of error in the problem as well as our level of confidence. The one thing we're missing is our p hat. Because we don't actually know what p hat is until we conduct the study, we then have an algebra problem. So there are one of two ways they kind of address this. The first one is using an estimated p hat based on previous studies. So there would be wording in the problem that would indicate that. The second option is to use a conservative p hat of 0.5. And the reason they use a p hat of 0.5 is it gives the largest possible margin of error for any given z or n. We are most of the time going to be using this option. So you'll either be given a previous p hat or you'll use 0.5. So let's look at an example. So before conducting nationwide polling prior to a national election, most good companies will decide ahead of time how many people to include in the poll based on a particular margin of error and confidence interval. Let's say that Gallup wants to conduct a poll to see what proportion of the voters would vote for Trump again if Donald Trump were running for president against Elizabeth Warren. Gallup wants to be 95% confident with a margin of error of no more than 3 percentage points. How many people must they randomly sample in order to achieve this? So I needed to identify 3 things: my z critical value, my margin of error, and my p hat. So let's start with our z critical value. If we want to be 95% confident, our z critical value would be 1.96. Our margin of error is 3 percentage points, which we will write as a decimal, 0.03. And then for our p hat, we're not given a previous one, so we'll use 0.5. Now we plug that into our formula. So we have n equals 1.96 over 0.03 squared times 0.5 times 1 minus 0.5. And then I just plug that into a calculator. And we get that n is 1067.11. Now, because n is a sample size, I can never have a decimal sample size. So we are always going to round up. No matter the decimal, we will always round up. That way we have enough people to meet our margin of error. So n is about 1068 people. Let me know if you have any questions about confidence intervals in general or constructing a confidence interval for a proportion.